Hi, so this is a video editorial for the LeetCode weekly contest 501. The problems were kind of straightforward this round. I had some silly mistakes and some implementation issues, but overall I'd say this was on the easier end. Q4 I guess had some decent ideas, but that the constraints I guess allows for some easier solutions to pass. But all right, so I'll be going through the problems in the order of their appearance, and after I go through my explanations, I'll attach a the live solve section where you can see how I approach the problems with my implementations in the live contest scenario. Okay, so Q1 was trivial. Basically, for some numbers input array nums, we just had to reverse and concatenate that and return that, right? So like for 1 2 3 we had 1 2 3 3 2 1, and for 1 1 we had 1 1. So for this we can just make another array x, which is reverse of nums, and then just append that at the end of nums and just return that. So yeah, this was my solution. Obviously, Q2 was had some implementation issues for me. I did not consider some cases, and even understanding the problem took me a while. So basically, and obviously, like for Q1, the constraints were less than equal to 100, but that solution would work for 105 as well. Regardless, in Q2 we are given an array of strings, chunks, and then we have to form first of all a simple string S by concatenating the chunks. And after the concatenation, we have to find valid substrings. We have to find a word which is defined as a valid substring, right? And a valid substring must only consist of characters A to Z and can only include hyphens if and only if the hyphen at the both of its ends are surrounded by, what do we say, surrounded by characters. Like, so for example, uh, these examples are kind of the example cases for this problem were really bad. It took me a while to understand what did they mean by the valid word. Basically, what they mean is basically this is a good word, this is a good word, but this is not a good word because a hyphen is not surrounded at both of the ends by character, right? Similarly, this is also a bad word. Like if the because here on both of the only on one end the hyphen is neighbored by a character. Like here on both of the ends it's a edge word, so basically like there's nothing there, so this is also invalid. So then we have to get all of the valid words from here, and then for every word in the query we have to what do we have to do? I forgot. We have to find the number of occurrences of word, right? So finding the number of occurrences of a string in this, my idea was first of all we can parse this into a string which has all the valid occurrence, then we can store that in a try, and then we can query it, right? And even a try is also not needed here. We could just put that in I guess a map, and that would work as well. So wait, let me get the reference. Yeah, I think the map solution would be better. I have no idea why I put that stuff in a try, but no worries. 1 second. Just one session. 210. Yeah, obviously the map solution would work as well. Regardless, basically, we can just parse the input string into the uh, uh, what do we say, valid words, and then just map store those frequencies of every word in a map, and then just query them in O of log length of the word. In O of length of the word, since this has to be hash first, right? Yeah. I have no idea if I implemented a try for this. Like, A try solution is same as well. Basically, at the like if you want curious about a try solution, the try would store some word like this, right? So let's say we have a word bad, it will store it like this. We have B, we have A, and then we have D. So while inserting the words, I'll go to the end and I'll like store that, okay, this word, I'll count the number of appearances of every word at the end node, and then while querying, I'll go down, and if that node exists and say end node, I'll just return the count from there. So that was the try solution. And map solution is simpler. Like you just parse the input into parse string of parsed characters and then increase the frequency, and then for every I just get the value. And this is my implementation for parsing. I'm pushing back a empty space at the end so I don't have to handle S cases. And first we just concatenate all the characters, right? Now if it's an empty space, what we do is if the current word we were dealing with was non-zero, then first of all we have to check that the dash is not appearing twice, right? So my parsing logic was basically, let's say for an easier case, like we'll store the current word in some char as soon as we find a space, and I have also forcefully appended a space at the end of the string. As soon as we found a space, first of all, what we like here, the cur is when we reach the space, the cur is ABA, right? So this can be pushed into our result. Let's say if we had something like this is hyphen, and then a space after this. So in this case also it would work since we can just append this. But if we had something like this, and then we have a space, and then C. In this case, ABA hyphen is not a valid word, right? We have to remove this hyphen. So for that case, I'm checking if the cur has a size and its last element is hyphen, then we remove that and then we push that. Else, if the character is not a hyphen, we'll always push it. But if it is a hyphen, then we have to check if the previous thing was a hyphen as well or not. If previous was not a hyphen, so something like A hyphen B hyphen C, something like this is valid, right? So here previous was not a hyphen since car was A, so this becomes this. When we go to this is always appended, and then we go to this. When we go to hyphen, B is not a hyphen, so we append this, and so on. But in the case of a previous being a hyphen, what we do is we see that like something like this. Here this section till here is valid. So in the current we have this. Then we put this, we see previous is not a hyphen, so this is appended. But when we reach this, we see the previous is a hyphen, right? So what we know is, we know its previous section would be valid. So we can pop back its current. Also, we have to make sure that cur is not empty. But that wouldn't matter assuming all of the queried words are greater than equal to, all of the queried words are greater than equal to one size. So this wouldn't matter, but should have done this as well. Car.size. And this was due to, it was mostly an implementation problem. Q3 was kind of interesting, I'd say. Basically, we are given an array nums and we can perform the operation any number of times. Just choose two indices such that nums A is divided by nums B, and then replace nums A by nums B, and we have to find the minimum possible sum. And of course, n and the values are less than equal to 10 power 5. So an observation here is, what is this operation? 1 second. What is this? Yeah, all right. So what is this operation? If you are replacing some element x with some y such that x mod y equal to 0. This basically means you are replacing x by its factors, right? And if we had free reign, then what we would do is we would replace x with its smallest factor, since our end goal is to minimize the sum. But we can only replace x with y if y exists in the array, right? That's if some y exists in the array. So basically what we are doing is, for every x, we want to replace it with the smallest y with exists in the array. And since this much we know, like we have some intuition of the operation, now what we can think is like, let's say we have some numbers here. Like obviously what we would want to do is we would want to go to the largest number first and then replace it with the smallest number. But this order, yeah, my bad. So basically, like we would like the way how I implemented it, what we would do is we would go to the largest number first and we would replace it with the smallest factor which appears. Like here, 8 would get replaced by 2. So this would become 2 and this would also become 2. Because of my implementation, I have to follow this order as well, because like even in the example statement, you can see like they are replacing the largest value first, right? So this also gave me the hint, like in some cases, in some implementations, I don't think the order would matter, but the way how I implemented it, what I'm doing is, first of all, I'm pre-computing all of the factors in n log n. I'm sorting it because largest first. And what I'm doing is, I've pre-computed the frequencies for all elements. Now for some number and some its factor and all of its factors, if factors would obviously stored in the increasing order. If the frequency is non-zero, that means it exists in the array. Then I'll add it to the answer and break. And at the end, I'll do this. I'm doing this because, like, let's say we have some number 7 and then we have some 3. 7 has no factors, right? I mean, no other factors than like 1 and 7. We have this for 7. So, like, here in my frequency, I will have 7 with 1 and 3 with 1, right? So, while iterating on all of the factors, 1 would be 0. But since I have not done this operation yet, this one, at the end, I would know like this is for substituting for no replacements, right? Like if I lead 7 as 7, that means I haven't done any replacement. And since I'm doing this, my bad, since I'm doing this minus minus operation on at the end, so this will get like, this is always bound to happen, this thing. So yeah, this was my implementation for Q3. This I found it to be easier than Q2, honestly. And Q4 was like Q4, the idea was simple, and the solution, my solution is simple as well, but I made some implementation mistakes, so it took me some time. But basically, what we are given is this roads, where roads is the bidirectional roads, where roads is the source and not source and destination, the endpoints, the cost and the tax. And basically, the cost is the cost to traverse the road without carrying apples, and tax is the multiplier for cost with carrying apples, right? And what we have to do is for every shop, we can either buy the apples locally for prices high or travel to some random shop J using any number of roads, right? Buy the apples for the price which is available there and then return. Now, since we are carrying apples, we have to pay this. Obviously, the path can be different, doesn't matter. And now what we have to do is, for every answer, we have to just find the minimum cost, right? So my implementation is kind of messy, but the idea was straightforward. Wait, let me clear this up a bit. So like this, and the constraints, obviously. Constraints were interesting. N was less than equal to 1000 and M was less than equal to, obviously, like the max possible number of edges or 2000. There won't be any repeated edges and self loops. And so, since this is obviously a graph problem, like you have to infer that this is a graph first of all, because we are given a shops and roads. Basically, the shops would be the nodes. In this problem, the shops would be the nodes and the roads would be the edges, obviously. So we can construct a graph. Oh my god. We can construct a sort of a graph. And what we have to do is for some nodes, for some source node, either we buy the thing here with prices source, or we go to some arbitrary node, let's say this one, or we go to some arbitrary node this by paying the costs till here. Then we buy the apple here for prices, let's say J, and then we return paying the double cost, right, with the tax and all. Hmm. So first of all, let's say some J is the answer. The answer is basically this, right? And let's say source is I for now. If we obviously the at least at most the answer would be prices I, because like if all of the costs are more for other nodes, why would I pay more? I can just stay here and buy it, right? So this is the maximum value of the answer. Now what we do is, if I'm going from I to J, we have some distance I to J, right? This is without tax. Then we are buying the thing at J, so we have prices J, one second, prices J, and then we have the distance from J to I, but this is with tax. So let this dash. This is the blue lines. Let me color it as well. This is the distance I to J. Then we have the prices and the blue lines, right? Since n was less than equal to 1000, what I did was for every I as a source, I pre-computed the non-tax distances, which means starting at 0 and iterating on all of the normal edges without paying the tax, just the cost. I computed this distance in a 2D array right here. This, where is it? This distance A to B is this A is this. So I comma J would tell with I as a source to reach J what is the minimum possible distance. Now, when we are returning from somewhere, we would have already bought the item, and we would be paying the tax as well, right, in the edges. So that is in distance B. Distance B is actually inclusive of both of these. So like in Dijkstra's, what we do is we initialize the source with 0, right? Source distance will be 0. When I'm already paying for this item, I initialize the source with prices J instead of 0, since we would be already paying that. And then on top of that, all of the edges I considered was with the tax. So here is my implementation. And then obviously the answer would be either this or the J with the minimum this value, right? And so my implementation was basically I created two graphs. One graph A was the one without the tax, and the other graph was with the tax, where I am multiplying the edges. Here, this is just my Dijkstra thing, where if operation is 1, if OPN is 1, that means I have bought it yet. If it is 0, I haven't bought it yet. So this is initializing it with the proper initial value. And then I'm just doing the Dijkstra's, normal Dijkstra's iteration. I initialized all of distances A with the graph A values, and I have not bought the thing, and the graph B with the tax values, this B, and I bought the thing. And at the end, the minimum value is either this, obviously, or I minimize it with respect to this. I first of all go to J, and then add this B, as I stated already, account for this buying, right? So, or I go from I to J, then at J I buy, and then return to I. And obviously I minimize this. So yeah, this was my solution for Q4 and all of my problems. And like my implementation was definitely weaker this weekend. I can't tell that, but I guess we'll see. All right. After this, you can see how I approach the problems in the live contest. All right. Bye. रिवर क्यों है? लाइक व्हाट? मैं सीरियस हूँ, रिवर क्यों? ट्राई से कर सकता हूँ इसलिए। अरे यहाँ पे अच्छा, ठीक है।